right, I'm going to switch gears. Sahir Ali, we met him through Todd Rupert. Turns out I found a WhatsApp chat from 2 years ago when I connected him. I met him in Singapore as well. But he is on riding the wave of something called TechBio, which he's going to explain to you. We're in a, this is the good, you always talk about the positives of technology. This is the poster child. Sahir Ali, over to you.
Well, thank you, Mark, and good to see everyone here. I've got 15 minutes. It's an intersection that is very interesting, but I'll try to condense it in 15 minutes. But I guess what we call by TechBio is that there's this profound convergence of technology in biology, particularly. And traditionally, biotech has been thought of, we find a molecule in microbes and such, and then we sort of take it out and we'll see what actually sticks in therapeutics. Ultimately, what has happened over the last 2 decades with certain technologies coming together, and now with AI, biology itself is turning into technology, and it's turning into an engineering discipline. And so I want to walk you through a few things I have. And so, Mark, if you don't mind, I will share some screen. I'll walk through a little bit. I think hopefully I'll give you a flavor of what's actually happening. It's not just AI, it's not just technology, but I think there's an entire sort of paradigm shift on how we even think about what human disease actually is. And so let me share my screen here, and let's quickly go through this.
Is that a real screen behind you, or is that is that at your real office?
Yeah, it's real. Okay, so when Human Genome Project was completed, Craig Wetter had profoundly said that this will be the century of biology, and perhaps the notion for that was that we've seen these techno-economic discontinuities because there's these sudden jumps that happens when certain convergence happens, and we've seen that with the combustion engines and electrification when we discovered the electrons and we transmitted that. And so I think something similar is happening at the moment with what we call AI-powered science, particularly in biology. And so if you look at sort of the trajectory of human creativity quotient, it took a long time to come up with a framework called science. And after the science, the sort of the engineering of the machines, and with the help, we've kind of made a lot of progress. But over the last 10 years, we've seen some profound breakthroughs, such as the AlphaGo, which was a breakthrough in reinforcement learning, which led to the transformers and the ChatGPT. But in 2021, we also saw a pretty massive breakthrough, which was actually termed as the breakthrough of the century, which was AlphaFold, which actually used previously compounded technologies and collections of data, and then generative AI to predict 200 known million proteins. And that was a pretty big moment. And so what we're staring at is what actually happens when all of the previous compounding of what we've seen in technology, the data, and everything else, and understanding, and we're looking at a kind of a hockey stick curve. In fact, ultimately, where we're really heading towards is this notion of what does AI-powered science looks like. Currently, we have about 300,000 human scientists. And with this convergence, you'll start to see that perhaps I think the biggest implication of even just purely from the perspective of what AI can do is actually augment our capabilities in actually doing something in what I call engineering life. And so if we take a step back, the whole purpose of why we're so interested in biology and everything else beyond manufacturing and everything else, it's our own life, which is human disease. And about 140 years ago or so, actually, interestingly enough, electron and the concept of a cell were discovered around the same time. And if you look at human disease, we've known for almost a century that human disease is nothing but cells being lost and cells malfunction. It's really manifestation of these two things that causes human disease. We've also come to understand that aging is actually a disease. And so over the last 100 years, we've known that if we could tame the cell, even a single cell in our body, we could perhaps engineer life, we could eradicate disease, we could have cures and all. So what has happened over the last 140 years is that we have learned to manage some disease, but we've not been able to cure pretty much not a lot of things at all. In fact, we've done very well with infections. In fact, There are 10,000 plus known somatic human diseases. We only target 500 of those today, and that's been the story of what we call pharmaceuticals and biotech. Uh, but if we step back and take a look at what happened to the electron, which also is a subatomic, a small particle, we've actually done quite well creating engineering sort of platforms to really tame the electron. So if you think about what we did with the hardware sort of revolution, we learned to sort of read and digitize what was happening with the transmission of electrons, which allowed us to write back through software. And that engineering abstraction really sparked the digital revolution we call information technology, which of course led to all these platforms, and which essentially gave rise to VC asset class to begin with the chip, with the personal computers, the internet, the mobile computing, and then the artificial intelligence. And so we've really, at the end of the day, if you look at all these platforms and the billions of economies that came out of this, it's really about engineering an electron. So the idea is, why can't we do that with a cell? If we could do that, we could engineer life, disease, and everything else. And so the first big step towards that was actually in late 1960s, where we figured out that in a human cell, there is something called an information flow, and that was known as the central dogma of life. What eventually happened is, in a cell, we have DNA that makes the RNA, RNA makes the protein, and that protein then functions everything about life. I just blinked, that process just happened. But what has happened over the last 2 decades is that we've actually digitized this entire stack, what I call a biostack. And that has been sort of the missing piece for a long period of time on how to actually start to interrogate this entire information flow digitally. In fact, we started this century with a very big milestone. We finished Human Genome Project. Now, a lot was said about Human Genome Project, where we understood, what the human DNA markup is. But I think more importantly, it was actually it ushered the era of digital biology. It actually digitized a molecule called DNA, and we could now read this digitally. And so that, after a very long period of time, biology has actually introduced a technology platform called next-gen sequencing. So Illuminas of the world and all. And that was about 23 years ago. And that ushered what we call digital biology. So not only we can read biology and understand it, but now we're producing massive amounts of data, just like what we had started to do with engineering disciplines on electron, the microchip, and things like that. If you compare that to how fast the computing technology was evolving from 1960s to now nanoscale, we call that Moore's law. Perhaps even faster is this idea of digital biology, where how fast and cheaper we can actually read into this biostack, the genome, and everything else. So in fact, we've gone from $3 billion 20 years ago to $300 before COVID. And now the cost of human DNA sequencing has now dropped to 100. And in about next year and a half, 2 years, it might come down to $30. So that arguably could be the fastest learning curve and may amount to largest price decline in the history. So this actually sets up a big base for how do you turn this entire discipline into an engineering discipline. So now, over the last 6 years, we've also started to see an emergence of truly biology becoming the technology, meaning how to engineer the cell. We call this cellular reprogramming. And if you look at the Nobel Prizes given over the last 6 years, just 5-6 years, Jennifer Doudna received a Nobel Prize for CRISPR. We can now go into the cell, we can edit the DNA and eradicate the disease. So in December 2023, we saw that sickle cell, which had no cure, CRISPR can go in and just edit the disease out like a digital circuit. And that was quite profound. And we've now seen this now in human. Jim Allison, who's pioneered immunotherapy, in his Nobel Prize in 2018 said, instead of taking drugs, we should be just able to give patients their own cells that can fight cancer. Immunotherapy was that. And we just, the micro mRNA Nobel Prize. So we're starting to see this convergence happen, where we're now starting to take a look at how do we actually start to engineer the cell. Finally, if I give you a big picture of what's happened, is there's something called a biostack, just like a technology stack. And that stack starts from DNA to RNA to protein to cells to tissues to organ and the organism, which we call health. At each of this stack, we can now read and write. Just like if you think about the 3 R's of the technology, read, write, reprogram, we actually have fundamental breakthroughs over the last 20 years that now we can read and write. So if I just quickly walk you through on the DNA level, you may have heard of sequencing technology, which reads what's in there digitally, but we can write through CRISPR and gene therapy. If you look at the RNA stack, which is where 80% of diseases manifest, we can now read that through RNA sequencing. These are public companies, by the way. We can write back onto the stack. So during COVID, mRNA vaccine shot was a right technology. We could target that layer. In fact, that opens up 79% of undruggable targets because we can write to it directly. Proteins, we can read it through protein sequencing. It is fundamentally the function of life. We can design new proteins through AI that nature hasn't been seen. On the cell level, we have imaging technology that we can look at the state of the cell, and we can start to address why certain cells shift. We have cell therapies to write onto the cell, tissues. At the sort of organ level, we have in silico model designs. We can actually create digital twins of the organs. But also to write back, we have stem cells that we can start to do regenerative medicine. And on the organism level, we call this personalized and precision medicine. And so we've now sort of seen the breakthroughs. And just like any breakthrough, this is where the big inflection point starts to happen. Now, artificial intelligence is a big component to a lot of that. As we know, it's an irreversible and inevitable trend. It has been adopted faster than the computers and internet now at this point. The developers of neural networks won a Nobel Prize last year. For the first time in physics, a software system got a Nobel Prize. But more importantly, at the same time, the second Nobel Prize was given in chemistry to AlphaFold that predicted 200 million known proteins. This was termed as the most important achievement of AI because just to give you the sense of the scale here, before AlphaFold, humanity only knew 200,000 structures of protein. And within a year or so, it predicted 200 million. Just the amount of inflection point that has. And Google CEO tweeted, I think last year, that 2 million people are now using AlphaFold. That number is just insane. So finally, one last thing I want to leave you with is that if you think about this bio stack, what has happened is we digitized this entire stack, and what really comes out are these digital sequences. And just like our text, just like our images, these are sequences that we can interrogate. And turns out we have a tool called generative AI that just works very well on sequences. And because of that, we've started to see synthetic biology. We're starting to do early disease detection through AI, novel diagnostic and prognostics. And really what we're talking about is the sequences of life that we can engineer and not only look at disease cures, but also it has profound implications to this, what I call a $3 trillion market space, from digital health, AI-driven medicine, multi-omics, personalized medicine, synthetic biology, cell and gene therapy. It is a huge market space. And in fact, if I was to actually just give you what really is the convergence of this market, it is AI, sequencing, and cellular reprogramming. And it currently, as it exists today, there is a market already. Precision therapies, 25% of all of FDA-approved drugs now are classified as personalized and precision medicine. Multi-omics technology. By 2030, 100% of all drugs will be developed using some sort of digital biology. It is the same moment where software companies stopped producing CDs and sort of started to make SaaS products. Programmable biology, today it's a $30 billion revenue stream. This is the mRNA and sort of gene therapies and all. But it actually unlocks 79% of diseases that we couldn't touch before. Huge inflection moment. And AI and healthcare and medicine. I just want to leave you in one stat here. The third reason anyone dies in the United States, third or fourth, depending on what survey you look at, is medical errors. And the medical error is not just physicians, but it's the entire systemic things. There are low-hanging fruits, which is reflected, by the way, in that FDA over the last 2.5, 3 years have now approved 1,000+ AI algorithms. And that's the current state of where we are. Finally, Biden government had signed an executive order, I think a year and a half ago or 2 years ago, called bioeconomy. And they recognized that what the implication of this biostack I'm talking about, from digitization and AI and reprogramming of the cellular state, has actually consumerization that is growing at 8% CAGR. By the way, I think Ozempic is that story. Ozempic is absolutely a consumer story. There is a $1 trillion market space where it has actually started to create manufacturing efficiencies. We have seen companies that are taking low-grade brines of lithium and turning it into high-grade using enzymes found in human bodies using our AI. We've seen companies that are using clothing dyes that are more efficient and more environmentally friendly, that is produced through perturbing the bacteria, just like we had figured out 40 years ago to do that to produce insulin. So there's a bioeconomy at play. And finally, some of these platform technologies and engineering actually are finding market adoption because there's a patent cliff in big pharma. Over the next 5 to 6 to 7 years, there's roughly 30% patent cliffs. So these patents are expiring. That number we have never seen before, because most of the therapies and drugs that exist in market today have been introduced over the last 15 to 20 years. So those are expiring. That is about $200 billion at risk. By the way, this screenshot here is from 2023. So it does not even include Ozempic, which is also set to expire in the next few years. So there's a lot of market forces on why these technologies are started to find sort of that hockey stick curve. And finally, if you look at the biotech acquisitions over the last few years, even during this downturn, cancer and immune system, this is where really the engineering of the cell is required, is now extremely robust, even during the down market, because that's the only way. This is an unmet need. If we want to tackle aggressive disease that we have never before, these are the technologies that are going to make it happen. And finally, what this means for us as humans and life is that we have known for 100 plus years that human disease is cells being lost and cells malfunctioning. So what we're starting to do now is, if cells are lost, we're starting to replace them using iPS stem cells and all. If cells are malfunctioning, we can hack and correct them through CRISPR, gene editing, mRNA and all. Ultimately, what we're starting to do finally for the first time is human cures. That's the landscape. I think I did that within 15 minutes. I talked very fast. So Mark, I'll stop here.
So if I gave you $100 million, and you almost have $100 million, right? What are you going to invest in, given this landscape?
I'll give an example. One of the biggest challenges of our lifetime is that we cannot cross blood-brain barrier, the CNS disease, which is, massive. And turns out that a lot of the CNS diseases, neurological, Alzheimer's and a bunch of other things, it's because there's a particular gene missing. So if we could deliver that particular gene into that affected areas of the cell, we could not only reverse the disease, but maybe cure the disease. And turns out we have technology called gene therapy, and we're not able to go in there. And so we're backing a company that actually delivers that into the brain, that unlocks this entire space, is something that is absolutely a convergence of sequencing, the genomics understanding using AI and all of that, right? So that's one area. The second is early disease detection. 1 out of 2 women in their lifetime in the United States will be diagnosed with cancer. 1 out of 3 men will be diagnosed with cancer in their lifetime. Where the burden lies is that these cancers are not caught early enough. There are technologies now using the same convergence of 3 stack I told you, where we can just draw the blood and you can actually start to look at what is floating in the blood, because every cell dies and it disintegrates in the blood. Same thing with if there's a cancer growth, it may not be detected by MRI yet, imaging or felt or any of that symptoms. However, it's floating and the signals are floating in the blood. We're starting to find them through AI. There's a company called Grail, but that was an early sort of technology. Now we are starting to see methylation patterns on that. So early adoption, early cancer detection through commodity tools like blood is starting to find a huge importance. So I think that's one area. And lastly, I would say that if we're targeting certain diseases and engineering life, it's the same moment as iPhone couldn't have come about if we didn't design new hardware. So for example, new touchscreen concept or new software. It's the same thing as if we have existing proteins that we know and we keep trying to retarget those. De novo protein design is an entirely AI field where AI is helping us design proteins that we have never seen before. And so it's the same thing as how do we actually start to do first principle design. So that's one other area. Just some.
I appreciate that.
Yeah.
I'm excited to work with you.
Thank you, guys. I know I talk fast, but Mark had only given about 5 minutes, though.
Yeah. Stick around. We're going to add some more voices here. But Wojciech, you had a quick question?
Yes, Sahir, how far are we from synthetic microbiome?
Yeah, that's a good question. I think first we need to fully understand microbiome, and I think we're starting to get a bit closer to that. Mike, as just for so everybody know, microbiome plays a very big important role because we as humanity has evolved alongside bacteria. We have billions of those in our stomach, so we can link them to mental health and all. So I think that again, the same stack that converges with digital biology, AI, understanding, I think that's where we are today. We're starting to understand microbiome really, really well because there's more data, there's AI that helps you understand. However, where we're not gotten to it is this reprogramming of the microbiome. And I think we're getting there. And I think that's going to be very important for us to solve some important health issues and things. So synthetically creating those, I think early stage.
Adam.
Yes, Sahir, great presentation. My question to you is, can you give an example of a protein that you would create and the purpose of that protein that we've never seen before? Would that be used in plants? Would that be used in people? For example.
Oh, that is a fantastic question. In fact, if you want to look at, there's a company called TechBio, AETHR. They're doing exactly that. So away from biology, what are some of these proteins and ultimately that turn into enzymes we can use to make some manufacturing process efficient? So one of the things they're tackling is PFS in the water. We have known that we cannot remove it completely entirely from the water, but with that de novo design protein that nature hasn't seen, we could actually tackle that. I think the example I was giving was the lithium, a low grade to high grade. It's a similar vein, but on a therapeutic side, we can actually design new protein that what is the real need today in the moment? If you ask me, what is the need for new protein design that nature hasn't been seen? It turns out in the world today there is something called antibiotics crisis, which some of you probably know about, right? And what has happened? What's happened is the antibiotics that were discovered 100 years ago now are resistant in our bodies, right? The bodies have evolved, and we don't see that problem in first world. But you go to sort of developing countries where they don't have the next treatment, next pill concept, people are dying. And so there are companies, in fact, there's one company I've invested personally from the fund, is they're pinging this AI system that says, okay, well, we want this protein to do exactly what this previous protein did, but make it the same efficacy, don't violate the patents, but also resistant to the body, and out comes protein design. And that actually starts to be less resistant to the body and things like that. That's an immediate need. But in certain areas, I can tell you that there are certain cancer, certain aggressive diseases that we just don't have those targets, and that's where a slew of companies working on. Hope that answers the question.
Thank you, Sahir.
Samir?
Yes. So Sahir, a question, which is bioethics, right? So potentially we have tailor-made babies, right? We have the potential for sub-splitting of the human species into subspecies based on whatever super characteristics we can program into specific biomes for our families. I mean, this is where it's going, right? So what are your thoughts on the bioethics of splitting the human race into all these different genetic subspecies?
I think the designer baby was a big concern. And I think historically when that happened was the first time ever a gene editing conference happened. That was 2017. And a Chinese scientist came and said, look, I just tried to edit the embryo. And I think what eventually we realized is that we needed some guardrails on what is therapeutics and non-therapeutics. And I think including China, including everybody else, has understood that therapeutics applications of these are where we are today. I think at a complete embryo level, we're still far away, but I think we have guardrails built in on who is able to do these non-therapeutics versus therapeutics. But I would say that every technology in the beginning will have these bad actors that will try to do this. But my hope is that with the global bodies coming together, we're starting to put some guardrails. And we have done that with therapeutics of molecules and nuclear technologies and such, and I think we will do the same here. But if you ask me, we're very far away from saying, how do we actually create designer babies, which ultimately could be a possibility. But I think we're really focused on what is the unmet need, is can we cure disease?
Don?
You hear me okay?
Yep.
Okay, great. Here, amazing presentation. The stats on women and cancer really has my attention. I guess my question is both personal and from an investment standpoint. I'm curious on the rising number of women in the USA who take Ozempic, not just for weight loss, but as a lifestyle. So they're not on it for just a few months or a year, they're on it for several years. And I'm very curious to know what your opinion is on the health consequences of this, if there are any, or if you think that it is the wonder drug. So we have Ozempic, we have trizepatide, and then I'm hearing more and more about another type of peptide treatment that isn't one of these first two that might offer benefits. But I'm just curious on what your thoughts are on long-term use of these drugs, number one, and number two, if there are actually supplements. We both know that tons of supplements promise the world that this will be your next GLP-1 drug that is more of a supplement than it is a paid for drug.